worship, but all right, so we'll start with today's lecture, which is about QED. So until now we did all the general formalism of quantum field theory, and from today on we'll start with applications to physics, to real physics, which means for this QFT1 class just QED. So we'll describe what QED is and its Feynman rules and path integral, and then identities among Green's functions that are a generalization of the Ward identities that we found, which are called Ward-Takahashi identities. So first of all, what is QED? Means an abelian gauge field that stands in for electromagnetism. Coupled to fermions, standing in for the electrons. But for completeness, I'll consider also a little bit more general story. It's used to simulate, to make some easier statements about QED. Since fermions are slightly more complicated, one sometimes considers complex scalars also couples to them, so we'll consider that as well. All right, so let's define things. So as I said, we have a Lagrangian involving a fermion, a Dirac fermion. And the complex scalar, both of them couple to an abelian gauge field. So in Minkowski space, we will write what? Minkowski space, we would write kinetic terms. So for the abelian gauge field, we write -1/4 f min nu squared. Then for the gauge field, we write minus psi bar, well, to be d slash, but now, since it's coupled to electromagnetism, is capital D slash plus n. And, well, a complex scalar as well. So let's say minus d mu phi star d mu phi. So these are kinetic terms. And then perhaps there's some possible potential for this complex scalar, which in order to preserve local Yuan invariance must be a function of phi star phi. And then here, as usual, d star is d mu gamma mu, and d mu is d mu minus I e a mu. And f mu is d mu a mu minus d mu a mu. What else? Psi bar is psi dagger I gamma 0 with my conventions. And then the gamma matrices satisfy the Clifford algebra with a mostly plus metric. Then, of course, as I said, we have local U1 invariance, which means psi goes to e to the I alpha psi, and also phi goes to e to the I alpha phi, d mu to a mu plus I plus I over E. Or if you want, maybe I can put E here, like in my notes. Oh, sorry, yeah, of course. All right. And of course, this local U1 comes from a global U1 at A min equals 0. That was gauged, that is made local. All right. So this would be Minkowski, and then, as we learned, for Green's functions it's more useful to consider the Euclidean space, whereas for S matrices we have to consider Minkowski because there's no scattering in Euclidean space. So in the Euclidean space, IS Minkowski is minus IS Euclidean. And then the Euclidean Lagrangian has positive definite terms. Positive definite terms only, so plus 1/4 F mu squared plus psi bar B slash plus n psi plus d mu phi star d mu phi plus d star phi. Okay. All right. Then, this being a gauge theory, so having this local U1 invariance, we have seen that we need to fix it in order to define a path integral. So to define a path integral, we must fix the local U1, which amounts to getting rid of zero modes or redundant degrees of freedom from the kinetic operator. And that we have done in the path integral through the Fadeev-Popov procedure. Which amounted at the end of the day to adding a term to the Lagrangian, amounts to adding a gauge fixing term so if we say, well, this is LA, this would be L of psi and A, and this would be L of phi and A. Then for the part that depends only on the gauge field, we add a term which in Euclidean space, so this would be plus 1/4 F mu squared, and in Euclidean space this amounts to plus 1 over alpha d mu A mu squared, 1 over 2 alpha, sorry. Yeah.
This EFF means effective.
I'm sorry?
This EFF.
Effective, right? Instead, we write some sort of effective Lagrangian in the presence of gauge fixing. So the point of adding this to the Lagrangian is that the resulting effective action, but not in the formal quantum sense. It's just effective in the sense of gauge fixed. After the action, because we need to do a partial integration. So after the partial integration, this is written as 1/2 a mu, and then an inverse propagator squared, which now is well defined, so it has no zero modes. So this is called the inverse free propagator, right? And therefore this photon propagator in momentum space is the inverse of this. So minus del squared becomes p squared. So g mu 0 is 1 over p squared times delta mu minus 1 minus alpha k mu over k squared. Okay. All right, so I've written these formulas with the complex scalar simply because, as I said, it's a useful thing to consider. Sometimes considering directly the fermions is a little bit more complicated, so we take as a toy model of a complex scalar. But actual QED is without complex scalars, so I will not consider it from now on. So then, okay, this was the SF of A. So then we can write a path integral for QED. Path integral that will depend on sources for the fields, in this case for A mu, for psi, and for psi bar. So the sources will be called respectively J mu, psi, and psi bar. So we write path integral over these fields, A mu, psi, and psi bar. And then E minus S effective of A, psi, and psi bar. And of course, also the sources, G, psi, and psi bar. And here S effective comes from an effective Lagrangian. Well, okay, so S effective is integral d for x. The effective Lagrangian that depends on H psi and psi bar. And then the source terms, usual ones, minus J mu mu, minus psi, psi bar psi, minus psi bar psi. And the vacuum expectation values of operators, or observables, let's say that these depends on the fields of the theory. And then, as usual, this is the path integral, let's say d A mu, d psi bar of O E minus S effective divided by the same thing without O. And Also, as usual, we define the free energy F by saying that Z, function of J, psi, and psi bar, is E minus F, function of the same. I remind you that this relation is from thermodynamics. The partition function is E minus the free energy in thermodynamics, and therefore, well, beta times free energy, but we use the same notation here. And then, moreover, we also have the effective action generating function of 1 pi. So the effective action, which is the generating functional of 1 pi diagrams. That is defined as the Legendre transform of the free energy. Say gamma of A classical, psi classical, psi bar classical is F J psi bar plus integral J mu plus psi bar psi classical plus psi bar psi classical. Okay, and the classical fields are obtained. The classical fields and the sources are obtained from taking derivatives in the Legendre transform. So taking derivative with respect to J, we get what? This is 0, and here we get df dj plus a mu equal to 0. So a mu is equal a mu classical. And the classical is equal to minus df dj mu. And similarly, dd psi bar dd psi bar. Well, sorry, to continue. Well, what did I say here? Classical is here. To continue the same logic, we'll consider first derivative with respect to psi bar, and then we'll have df d psi bar is equal to minus psi classical, and then dd d psi. Similarly, we'll get df d psi. From this, just now the only new factor appears because psi is on the other side. So when we differentiate, we have to first permute and get a minus. Together with this minus, we get psi bar classical. So these are three relations obtained by differentiating with respect to these guys. And then three more relations obtained by differentiating with respect to these guys. So d A classical, we get that d gamma d A classical. This is independent, and here we get J mu. dd psi classical with the d gamma the psi classical. This is independent, and here we get minus psi bar, and dd psi bar classical, become the psi bar classical. This is independent, and here we get psi. Okay. All right, so these are 6 equations relating the classical fields and derivatives of free energy and the effective action. All right. So now that we defined the theory, we should define the Feynman rules. Well, as we said, there are 2 types of rules for Green's functions and for S matrices. Now, for Green's functions, in principle, we could also consider the rules in Euclidean or Minkowski, but in the case where this is useful, this is kind of a theoretical concept, so most of the time we consider Euclidean space for Green's functions. And then S matrices in Minkowski, so let's say Feynman rules for Green's functions in Euclidean space. And again, most of the time, well, one does calculations, one does them in momentum space. Sometimes it's useful, especially for Green's function, sometimes it's useful to consider X space, but still the most common case is momentum space. All right, so Feynman rules means what? So we have the fields, the fermion field and the gauge field. So for them, we have to write propagators. The fermion propagator IP slash plus m. This still has an index alpha, so we would have alpha beta. And this can be written as before by multiplying with minus IP slash plus m, p slash squared being equal to p squared. We get p squared, p squared. No, wait a moment. What have I written here? Minus m, right? No, sorry, no, plus m, yeah. Because this is equal to minus IP slash minus m. All right. And this will be also denoted by just a line going from the direction of alpha to beta. And then we'll also have a gauge field, A nu, for which we've seen that the propagator is 1 over k squared delta mu nu minus 1 minus alpha k nu over k squared. And so an important point that I think was kind of missed by a couple of you in the exam. So when one puts an arrow on the line of the propagator, that means that thing is a fermion. Only for a fermion do we have, well, we have a difference between alpha and beta, between the initial and the final points. In the case of a propagator, for instance, for electromagnetism, for U1 gauge field, we can still put the indices mu and nu, but the momentum will be denoted by a line outside it. Okay, so it's important to remember this. So if the line is on if the arrow is on the fermion itself, it's on the line itself, it means it's a fermion. All right. So this is for propagators. Then we'll have the vertices. In this case, there's only one vertex, which is for fermion, antifermion, and A mu. Let's say vertex image psi data. And the fermion would be plus plus I e gamma mu alpha beta. The reason is in Euclidean space we have minus g, where g is the coupling, but the coupling term in this case is minus I times e times the integral of this a mu psi bar psi, right? So we have on 1/2 and then two terms, each comes with minus I e a mu. Right, so minus the coupling in this case means I e times, with gamma mu. So it means plus I e gamma mu alpha beta. All right. Then we also have to remember the minus sign for a fermion loop. And here, again, some of you forgot in the exam. This is important when you add diagrams. If you have a single diagram, of course, it doesn't matter because the amplitude is the probability is amplitude squared. But when you have sums of diagrams, it's very important whether you add them up or subtract them. Gives the possibility of canceling two diagrams. So this is important. Another thing that you've forgotten. So for the fermion loop, so the point is, all of these things, if you forget the rule, you have to remember that these things have indices. All of these things have indices, so you have to put the indices. Otherwise, the simple rule is that if you have a fermion loop, this also comes with a trace, right? So if you don't want to put these indices that I put carefully here, you remember that the fermion loop is an independent trace. If you have several fermion loops, you have several traces. Okay? Or otherwise just put the indices correctly, because this is better, because in this way, you don't make mistakes. I mean, in the exam, I think half of you made a mistake of when I put when I asked you to write a Feynman diagram with a fermion loop, I think only half of you did it correctly or so. Anyway, so these would be the Feynman rules for Green's function in Euclidean space. But then, as I said, well, we could consider, for Green's function, we also consider Minkowski space and X space, but they're not so common. The most common is Euclidean momentum space. On the other hand, we're talking now about something that has physical significance, so the relevant issue is actually S matrices. And S matrices means scattering, and scattering is only defined in Minkowski space. Cannot define scattering in Euclidean space because there's no on-shell states. All right. So how do we write the Feynman rules for S matrices? Well, first of all, we're in Minkowski space, so we have to turn these things into Minkowski space objects. So the propagator for the fermion just gains at minus I, and then the denominator gets a minus I epsilon. So it's minus I times minus I p slash plus n, or p squared plus n squared minus I epsilon. Okay? Yeah, and now I can absorb this minus I if I want to, and then this is minus p slash plus I epsilon plus I m over p squared plus n squared minus I epsilon. And then it's also denoted by a line with an arrow, the same thing. Then the propagator for the gauge field, again the same thing. It's minus I in front and minus I epsilon in the denominator. So this is minus I over k squared minus I epsilon delta mu minus 1 minus alpha k nu over k squared. And the vertex is now just plus E gamma mu alpha beta. So again, a minus I in front. Now further, we have this same minus sign for fermion loops. And, well, trace, as I said, for each fermion loop. I mean, this is not necessarily part of Feynman rules, but I put it because, you know, as I said, most of you forgot to think about the indices, and then, roughly speaking, you do it this way, you just a trace. I mean, I'm hesitant to put this as a rule because simply sometimes you will not have something so simple. I mean, you might have loops that are, I don't know, complicated. It's complicated to disentangle, and then you should really take care of the indices to get the right expressions. But roughly speaking, for each fermion loop, you have a trace. Okay. Yeah. Now, well, I mean, in both cases, I omitted the standard things that you know, that 1 over the symmetry factor, and integrals for all the loop momenta, right? I mean, when I wrote the vertex like this without 2 pi delta, I implicitly assume that I have only integrals for each loop momenta, which is the simplest form of the Feynman rules, the one with the less to right. But now in the case of S matrices, we have the extra complication that we have external lines. So we have contractions. If you remember, we have contractions with the external fields. So external fermions, these things come from contraction of some fermion with an external state. So this would be US of P. Then if I have psi bar, PS, this is V bar S of P. And reversely, PS psi. CS psi bar, which is just the bar of this, is therefore U bar S of P, and PS with psi, which is the bar of this, is VS of P. And we denote these as external, external lines. So let's say US of P is an external line, but then of course this external line is connected to some vertex. So this would be fermions, and here I can only have, in this case, the only vertex in the theory is with a gauge field. Strictly speaking, the point about the contraction is only until the vertex, the external line only until the vertex. So this is momentum P, and then reversely, this one would be, so for the electron, for psi, the momentum goes in the same direction as the arrow, but for psi bar, which corresponds to positron antiparticle, we have a momentum that goes in the direction opposite to the arrow on the psi. Okay, so these are denoted by lines coming out, and then these are denoted by lines coming in. So let's say U bar, which is just a complex conjugate, that is to say the mirrors symmetric, if you want, form of this. So let's say here I have P, and then this one is the mirror symmetric form of this. So this is these are the external lines. Okay? And then you can also have external gauge fields. So the contraction of a gauge field with an external state of momentum p and some polarization epsilon is just this polarization epsilon depending on the momentum p. And reversely, the contraction with the bra is the complex conjugate of this. And then similarly, we define this as well, I guess I denoted it with momentum in this direction for the first, and for the second, momentum in this direction. Or rather, no, this is wrong. No, it should be with the momentum like this, and here with the momentum like this. I'm sorry? No, it's just these are complex conjugates, so it's supposed to be mirror images. Right?
Okay, but if you could write the first one with the arrow pointing to the left, and you will just have to change the second to the arrow pointing to the right.
Yeah. I meant that on my notes I had the same direction, which is not correct. So. Okay. So these are the final rules. The last one is not strictly speaking a final rule, but it's useful. So if we exchange two external fermion lines, so two of these things among each other, it amounts to commuting two fermions, which gives a minus sign. So exchanging two external lines means commute two fermions, which means minus sign. So this is not a final rule. You know, it's not about writing a Feynman diagram. It's just if you have several diagrams, instead of just calculating everything from the beginning using these Feynman diagrams, you can just simply say this: if the two diagrams are related by the exchange of the order of fermion line constructions, then of external lines, then that amounts to just a minus sign in between the diagrams.
Professor, you have a physical explanation to why people started to write the arrow of a positron pointing in the opposite direction of its momentum?
Yeah. So this was related to the Dirac picture that I told you before. So the interpretation was for the positron as being a particle of negative energy, right? So remember I had e to minus ipx and e to the plus ipx. And this was plus I et, this was minus I et. Right? So I called this positive energy, right? And then this is as if I have an energy minus E, right? Okay, so that's an interpretation of a particle of negative energy. A hole in the Dirac sea was thought of as a positron. But now that the opposite point of view is a particle of energy E traveling backwards in time, minus t. Right? So hence
That backwards in time.
that's going backwards in time. That's the idea. Okay, so that's why if I write a photon splitting into an electron and a positron, I write it like this. So this is the electron, this will be positron. Okay, so when I write it like this, I can either think of it as an electron and positron, or as an electron traveling forwards in time and an electron traveling backwards in time. Okay, that's the idea behind this. And it also makes sense in terms of continuity, which is another point I want to emphasize for you when you write Feynman diagrams. You know, you see the continuity of fermion lines. The arrow never breaks or splits or anything. It doesn't stop, split or anything. So the arrow on the fermion line can be followed as completing a loop, right? It can only complete a loop or end somewhere outside as an external line. There is no other choice. Okay? So for anything else, like a photon just ends here in these things. But fermion lines, no. I mean, of course, if you think of them as electron and positron, you say, well, I created an electron and positron. But forget about this, just follow the line. Think of this going backwards and forwards in time. Then the line should always be like this. Right? Or otherwise ending up outside. But if it ends outside, it has to end in pairs outside. One going out and one coming in. There is no other choice. All right. Good. Yeah, I'm going really fast, but that's good. So now that we've defined the Feynman diagrams, defined the theory and the Feynman diagrams, the one thing remaining is to consider identities that can be obtained between various diagrams and objects. So specifically, what we will be looking at are these so-called Ward-Takahashi identities. And I already said this a little bit when describing word identities. So we said word identities are the reflection onto Green's functions of the invariance of the path integral under a global symmetry. So if you have a global symmetry, we derived kind of trivially some relations between path integrals, and from them some relations between Green's functions. Now, in the case of QED, defined as it was on the board, we don't have any global symmetries. And I emphasized that in order to write that word identity, I need to have a global symmetry. But instead we have a local symmetry. And correspondingly what changes, what replaces the word identities is this so-called word Takahashi identities. So this is the analog of word identities in QED. And this is for local symmetry. Okay, so specifically what we had have this transformation. And well, so here we have to remind ourselves a little bit of what we said for word identities. So we assumed the invariance of the path integral. But the invariance of the path integral entails 2 points. One is the invariance of the action, which is to say the classical invariance. Right? The classical action being invariant is the statement of classical invariance. But then we also have the invariance of the measure. And this I can call quantum invariance, because, as I said, in principle we have the possibility that quantum diagrams break the invariance, and the way we see this in path integral formalism is by the fact that the measure is not invariant. So let's say quantum diagrams break the symmetry. So in path integral we see that the measure integral, the stuff, is not invariant. So the non-invariance in the path integral is obtained through the so-called Fujikawa method, and this one is called the Adler-Bardeen Feynman diagrams. So the result is what one calls quantum anomalies. And well, this is something that's going to be treated in QFT2, well, if I teach it. So anomaly means just that. So it's a symmetry that is classical, but it's quantum anomalous. It's not respected at a quantum level. And for global invariances, actually there is no problem with that. There's nothing intrinsically wrong with having a theory that is classically invariant under some symmetry and quantum mechanically not. I mean, it's weird, but there's nothing wrong with it, and this has physical implications. You can find, as I said, there's some Feynman diagrams associated with this. So there's some Feynman diagrams that break this symmetry, but well, that's fine. However, the same thing for local symmetry is not good. It's actually bad. So quantum gauge anomalies for local invariance is bad, meaning inconsistent. And to see that, think about what this means. So classically, I have this invariance, del A mu equal d mu alpha, which allows us in particular to take A0 equal to 0. That is to say, to eliminate a degree of freedom, right? And so by using this local invariance, we see that one degree of freedom that a priori was there is actually redundant and can be put to 0. But quantum mechanically, if suddenly that is not true anymore, I don't have this invariance anymore, I cannot put this to 0 quantum mechanically. which means that I have a difference of 1 degree of freedom between the classical and quantum theory. And that's clearly absurd. What happened to this degree of freedom? So there's a difference of degrees of freedom in between classical and quantum theory. So that's a contradiction. But a priori, you could write a theory that has gauge anomalies. So that means that theory is actually inconsistent. It's not a good theory. Okay, so one has to consider only good theories that do not have these anomalies. Now QED is a good theory, but then there's one more point of view. One should choose a regularization scheme. I mean, I have not told you specifically what regularization is, but regularization is, well, speaking, a way of making finite the infinities that appear in quantum theory. So we have to choose a regularization that respects gauge invariance. Okay. Anyway, so for QED, the issue is not so much the theory itself, which is in fact free of inconsistencies, but a choice of regularization. But assuming that, we have that the path integral is supposed to be invariant. So assuming that, path integral is supposed to be invariant. And then, well, I just erased it, but anyway, you remember what I wrote. So the path integral was written as some measure E minus the action. Those those terms were invariant. This is the classical invariance, this is the quantum invariance. But then I have, or minus, S gauge fix minus S source. So these terms, the source and gauge fixing terms, those are not obviously invariant. So by imposing this condition, I get something non-trivial now. Okay?
Professor, the action, the classical action was invariant for global signatures, right?
No, local. Local, right? QED. This is electromagnetism.
No, okay. In this case, we are talking about local signatures, but what we...
Yeah, we're trying to derive the word Takahashi identity because the word identity is for global symmetries we derived them before, so we don't care about that. But right now we're deriving a different set, which is for, I mean, the set will be derived specifically for QED. You could generalize it, but the important point is that we're actually having a local symmetry, and as a result of the local symmetry, there is a gauge fixing term. So that's why this derivation is new and non-trivial. Okay. In the global case, there's no gauge fixing term. All right. So let's write this specifically. So 0 is the variation of the path integral is, well, as I said, there's the measure d a mu d psi bar, that's invariant, and also E minus minus S. But now I vary this whole thing, so I get the same thing that I'll call effective action, including the gauge fixing and source term. And then in here, in the denominator, I will get yeah, maybe let's call it epsilon. I get the variation of minus times the action, the effective action. As I said, the minus classical action, minus S classical, is invariant, so I don't get anything from that. And then the only thing I get is from the contribution of gauge fixing and source terms. So first the source terms. So in the exponent here, I would get a term J mu A mu plus psi bar psi plus psi bar psi. Okay? And now I have to vary these terms. So J mu is invariant, is a source. And then A mu varies into D mu epsilon. And then in here, also psi bar is a source, it's a constant, but psi changes. So I get plus I E epsilon psi bar psi. And then in psi bar, I change, so remember this is I E epsilon, and therefore psi bar, delta psi bar is minus I E epsilon x psi bar. So here I get now minus psi bar psi. And finally I have the gauge fixing term. So in my so this was minus 1 over 2 alpha d mu a mu squared. And varying it, I get the 2 cancels, so minus 1 over alpha d mu a mu. And then d mu times the variation of a mu, but the variation of a mu is itself d mu epsilon. So here I get del squared epsilon. Okay, so this is the resulting equation. Okay. So this was del z. Now,
Sorry, the last term coming from where?
the gauge fixing term. Okay. And so now we divide by epsilon because, well, we have to obtain a relation that's independent of parameters. Okay. And moreover, as usual, I have all these sources in here. Sorry, no, I have all these fields in here, a mu and psi and psi bar. And I can replace them. With, so since this is acting on something with J mu, A mu, and these terms, right? So A mu can be replaced as usual with dd J mu, because when acting on this, A mu replaced with dd J mu will only act on the exponent and will come down corresponding A mu. And the same thing for psi, replaced with dd psi bar, and psi bar with dd psi. Okay? So, dividing by epsilon and replacing these fields with derivative with respect to sources, we get what? we get, let me write first this term. So minus 1 over alpha d mu. Well, first of all, del squared epsilon. I can partially integrate. Yeah, this was, I forgot to write the integral, was under an integral sign. So I can do a partial integration. I have two derivatives to partially integrate onto this, and so give two minus signs so that sign doesn't change. So it's minus 1 over alpha del squared d mu. Okay, this comes here, and then a mu is replaced by ddj mu, and then ddj mu just comes outside this. So when I say ddj mu acting on this, but the measure doesn't depend on j mu, so this gets outside, and I'm left with ddj mu acting on z. Then this term here, again, I partially integrate the derivative, but then I get the minus sign. So this is minus d mu j mu. And now j mu doesn't appear in the path integral, so I take it outside, and I'm left just with the path integral itself, just z in this term, right? And then finally I have this one. Here I just divide by epsilon the way I did. I don't need to path integrate anything. And then I have IE. And the first term I have IE psi bar. And again, the path integral does not depend on it, so I get it outside. And psi was replaced with dd psi bar, which again is not in the path integral, so comes outside. So I have plus IE psi bar, dd psi bar. And then what remains in here is again just z. And in the second term, I have psi bar, which is dd psi. Sorry?
Should it be minus d psi?
Yeah, probably. Let's see. So I have psi bar, then psi. Yes, it goes past. Yes, sorry. So psi is replaced with minus dd psi, right? Because no. Yeah, no, the other one. Yeah, psi bar is minus dd psi. Yeah. So this one is okay, and then the second one is indeed with minus. So I have minus plus another minus plus. So so psi bar is dz d psi, and then psi, because as before I'm left with z. Okay, so this is the equation resulting from the invariance of the path integral. Now I can divide by z. And also remember that z is equal to e minus f, that is to say log z is minus f. So if I divide by z, then in here I have the derivative of log z, so ddj mu of minus f. The same thing here, dd psi bar minus f, dd d psi minus f. Okay, so we get minus is plus, so plus 1 over alpha d squared del mu del f del j mu, then minus d mu j mu, then plus, minus IE psi bar, and here I have ddf, dd psi bar f, minus sign was taken outside, and here df d psi psi. Okay. All right. But now I remember the equations that I derived before with respect to derivatives of the free energy. So I had relations defining derivatives of free energy and derivatives of the effective action, relating them with other objects. So in particular, df dj mu was equal to minus a mu classical. This was equal to df d psi bar is minus psi classical, and this is equal to plus, this is equal to plus psi bar classical. Okay, so finally we obtain that 0 is equal to 1 over alpha del squared d mu, well, let's put the minus outside, so minus 1 over alpha del squared d mu a mu classical minus d mu j mu, then plus IE psi bar psi classical minus psi bar classical psi. No, sorry. What have I done? Something is not right here.
Expression for sources. You have expression for sources, right?
Oh, yeah, sorry. Yeah, so yes, I want also to replace these things. That's all. So I also have that this thing is equal to del gamma. So psi bar is equal to minus del gamma del psi classical, and then this thing is equal to del gamma del psi bar classical. And so here now the minus is cancelled inside the brackets, so I have the same outside. And here I have d gamma d psi classical, and here psi bar classical d gamma d psi bar classical. All right, so let's write this down again. So minus 1 over alpha del squared d mu a mu classical minus d mu, and I can also replace j mu with respect to del del gamma with respect to a mu classical. Classical. And then, or equal to times IE del gamma del psi classical plus del gamma plus psi bar classical del gamma del psi bar classical. Okay. So these are called the word Takahashi identities. And another name for this is obtained if, so you note what has happened here. So now these are equations for the derivatives of the effective action. The effective action is the generator of 1 pi. 1 pi diagrams. Okay. So here I have only the first derivatives of the effective action. So of course that's not really relevant. The first derivative, it would be a 1-point function, which is not particularly interesting. But this is the first derivative without putting the fields to 0. So it's not the vertices themselves, just a derivative of the function. But then by taking further derivatives and putting the classical fields to 0, we will obtain relations between 1 pi vertices or functions, and these will be called Lie-Zan-Justin identities. So this is one person, this is another. Zan-Justin is a Frenchman who wrote this big Bible of a book that, like a Bible, is revered and kept safe somewhere in a cabinet by me because it's too difficult to actually work with it, but I look at it from when I have some questions. When I want to understand some higher purpose. Anyway. So these were the word Takahashi identities, but by taking derivatives and putting the fields to 0, we'll get the Lie-Zan-Justin identities. So let's consider one such example. And let's obtain a relation for the photon propagator. Well, if I want to obtain a photon propagator, the photon propagator amounts to 2 derivatives with respect to the gauge field. I have already one derivative here. Then in these terms I have derivative with respect to psi, so they will not obtain the propagator. So in order to obtain the propagator, I must take one more derivative on this equation. So let's take one more derivative on this equation and then put a mu psi bar to 0. Okay? Then we obtain what? Well, in here we obtain derivatives on a delta function. So minus 1 over alpha del squared d mu delta minus 1 over alpha del squared with respect to x d mu with respect to x, and then delta of x minus y. That's from the first term. Now in here we get d mu times the 2-point function, the del 2 gamma with respect to a. So minus d x mu del square gamma d a mu classical of x d a mu classical of y. Well, yeah, at a so y is 0. And then on the right hand side we get and then on the right hand side, if I put psi and psi bar equal to 0 after I take the derivative, you notice that the derivative with respect to a mu can only act in here on this, but then I'm left with psi as it is. But if I put it to 0, that means this is equal to 0. The same thing here. The derivative with respect to a only acts on this term, but then I put psi bar equal to 0, so this term cancels. So this thing is equal to 0. So that's my equation. And then this thing is the 2-point inverse propagator.
So the connecting propagator and the propagator are always the same thing.
I'm sorry?
The connecting propagator and the propagator are always the same thing.
No, but what I mean is that in the effective action, the gamma is, so this is effective action. Right? So this was equal to the so effective action. This involves 1 pi diagrams. Right? So this is the quantum version of the classical action. So it's the classical action plus quantum corrections. And as such is of the type, I mean, any kind of field, but here I'm talking about a mu. 1/2 a mu, and then here what I would write? Well, I would write g minus 1. Sorry, mu, right? If I would have the classical action, I would write g minus 1, 0. But I have the quantum action, so I have g minus 1, the inverse propagator, right? So this gamma mu nu is the inverse propagator for the full quantum action, right? That's the interpretation of this object. Now, what was this equal to? This was equal to the free inverse propagator, if you remember, plus the 1 pi, right? 1 pi, which I called p mu nu. Remember? Then the higher order terms starting with this were the same as the, so this was 1 pi, were the same as the 1 pi, right? Okay. But for the 2-point function, we had this thing that the effective action, the term in the effective action was the inverse propagator, the inverse free propagator, plus the 1 pi part, pi mu. Okay? And therefore, for this 1 pi, so this, what, if I want to call it 1 pi propagator, right? What really means is the quantum inverse propagator. Because it's the thing that appears in the quantum action. Okay? I mean, this is, yeah, I mean, it's not even 1 pi because it's like this. It's effective action propagator, right? This is what you would call the propagator coming from the effective action as opposed to coming from the free energy. Right? If it comes from the free energy, you call it propagator. Right? But it comes from the effective action, then you don't call it, well, this effective action propagator, if you want, is the quantum inverse propagator because it's the free inverse propagator plus quantum corrections. Okay. Okay. So taking a Fourier transform of this to go to momentum space. Taken Fourier transform, we obtain what? So a Fourier transform means that k squared goes to, so k squared, sorry, d del squared goes to minus k squared, and del nu, wait, the indices, no, that's right, yeah. Del nu goes to I k nu. But we have one free derivative with a free index on both sides, so the i's I will cancel. So I'll divide by I. And then minus del squared gives k squared over alpha. And then I have k nu, but I want to write this as an outside k mu, and then delta mu nu. Just that in order to get something similar from this first term. So here del mu is replaced with k mu, which is already outside, so minus, and then this thing was called g minus 1 inverse. G mu nu inverse. Okay. Okay, so the equation to obtain is this one, but on the other hand, I just reminded you in here what happens. So this inverse propagator, so g minus 1 mu nu of k is actually the free one plus pi mu nu, right? Just reminded you of this. And then this thing was equal to k squared delta mu nu, and then minus 1 minus 1 over alpha k nu. And so substituting in here, we have this minus this minus this. So you see now that I have the same, that I get the same am I? No, yeah, sorry. Yeah, I wanted to cancel the terms, but no, the first observation is that then if I multiply with k mu, so k mu g0 minus 1 mu. If I multiply this, I get k squared k mu minus then k squared k nu. So these first term cancel, and I'm left with plus 1 over alpha k squared k nu. So 1 over alpha k squared k nu. Okay? So this is just from the explicit form of G0 mu nu. Okay, so this times this gives this. But this is the same term as we obtained in here. So here I also have k squared over alpha times k nu. Okay, so the two terms cancel. So I cancel this against this. Okay, so the only non-trivial part of this equation remaining is the term with p mu. So k mu times minus times p mu minus k mu p mu equal to 0. All right. So our equation for the photon propagator gave us that the photon propagator, the 1 pi part is transverse. Okay. Just like yeah, so the quantum correction is transverse. Just like the gauge field is transverse, now we have that actually this 1 pi correction to propagator is transverse. But that means what? So if I have that k mu pi mu k is equal to 0, being transverse means I can peel out the tensor structure, the dependency terms of mu and nu. So I can write pi mu of k as this transverse part of k squared, or I guess multiplying by k squared is the same thing. Depends. Yeah. So I have this tensor structure times a function of k squared. So I could have chosen to divide by k squared in here and absorb the k squared in this one, but this is the conventional way. So you see, this Ward-Takahashi identity or Lee-Zhang-Jusien identity that I've obtained for the two-point function allowed us to completely solve for the tensor structure of pi mu, which amounts to reducing, you know, how many functions we had in here, a priori 16, to just 1, right? So that, you see the power of these equations. Instead of 16 functions, I'm left with a single one. Okay, so as a second example, I can also consider the n photon vertex for n greater or equal to 3. That is to say, I just keep taking derivatives in here. So instead of, here I took one more in order to obtain the second derivative of gamma, and after that I put the fields to 0. But instead of that, I can just take more derivatives, n minus 1 derivatives. So let's say dn minus 1 d a mu 2 classical of x2 until d a mu n classical of xn of this, well, Ward Takahashi or Lee Zhang-Justin. And then put a equals psi bar equals 0. Okay? So I look at the equation, then what do I obtain? So if I take further derivatives, right? So the equation before was that. I mean, there was also a part with proportional to psi and psi bar. This part, but this is still 0 because it's still proportional to psi and psi bar after taking all the derivatives with respect to a. So these terms still vanish. But now, when taking one more derivative with respect to a, this is a constant, so that vanishes already. So I'm left just with this term. And so the equation then is just d dx mu 1 of this nth order derivative with respect to a mu classical x1 until a mu 1 classical x1 until a mu n classical xn a psi bar equals 0. Okay? And then I also remember, so this was called the expansion of the effective action, 3 factorial, rather. 1 over 3 factorial times these a's times gammas. The gammas were the vertex functions that we talked about. So similarly, in general, I have 1 over n factorial, a mu 1 classical, a mu n classical, gamma n mu 1 mu n. So what I obtain then by taking this nth order derivative and putting the fields to 0 is just this gamma n. So this is gamma n mu 1 mu n. Okay. And then further, we are interested as usual in momentum space, so we take the Fourier transform. So d dx mu becomes k mu, in this case k1 mu. And so this was a function of x1 until xn. And now we get k mu 1, k1 mu 1. Gamma n mu 1 mu n of k1 until kn equals 0. All right? So that's the Ward Takahashi identity or Lee Zhang-Justin identity obtained in this case. So this also says that the endpoint quantum vertex is also transverse. Okay, so the endpoint quantum vertex, which by the way, for n greater or equal to 3, this is a purely quantum object, right? what this means is we have something like this. With n greater or equal to 3 external photons, which obviously does not exist in the electromagnetism. This is a self-interaction of photons. Photons don't interact classically, only quantum mechanically. So this is purely quantum. But this purely quantum vertex is still transverse. Okay? All right. And finally, we obtain what is the original identity derived reward in Takahashi. So these generalizations are actually by Li and Zhang Justin.
This would not be a vertex in the usual sense, right? There would be a lot of things in the middle.
No, it's a vertex. Yeah. I said that this is the quantum version of the classical action, right? So in the quantum version, I have this inverse propagator G mu, and then everything else is vertices, right? So the equation of motion for the classical fields, which are the quantum webs, is given by this. So this is really a vertex, an interaction between classical fields, right? It's just in the quantum effective action.
So for classical fields,
which are the quantum webs of the operators, right? So this is what, if you measure something, that's what you get, this vertex. Okay? So okay, this is extremely small, extremely hard to measure, right? But this effectively means that you have, self-interaction of light, right? It's just extremely small. I mean, you can calculate this, it's extremely small. So, all right. All right, so the final example, as I was saying, is the original Ward Takahashi identity, the identity actually derived by Ward and Takahashi.
this is the level of the effective action. This is self-direction. So is there something else, any variance principle of the effective action? Because
As I was saying, if in the absence of quantum anomalies and in the case of gauge invariance, we have to have no quantum anomalies, because quantum anomalies means that the theory is sick, is not consistent. In the presence of this, we have that the full quantum theory is locally gauge invariant. And the expression of this local gauge invariance is this equation. Well, this together with k mu equal to 0. So these two equations are equivalent, really equivalent, to the quantum gauge invariance. That's what quantum gauge invariance means. That this is true and that is true. In the case of pure gauge field interaction. In the case of interactions with fermions is what I'll write now. But in the case of pure gauge field interactions, this is what it means. So remember, gauge invariance is about reducing degrees of freedom as being redundant. So this, as you can see, this is the most obvious case. In this case, you can do something similar, but it's much more complicated. But in this case, it's pretty clear. So this transversality, gauge invariance means that only transverse polarizations propagate, right? That means transversality is also true at the quantum level, both here and here. And correspondingly, that allows you to reduce the number of degrees of freedom in the quantum theory. So instead of pi mu with 16 functions, I have just one function. And similarly, well, more complicated, but similarly for these vertices.
Isn't that strange that a priori you had 16 degrees of freedom, and with 4 equations that you wrote, we reduced it to just one?
No, well, they're not 4 equations, right? I mean, the point is, there are 4 equations at arbitrary k, right? That's the point. It's functional equations. They're not equations, right? So, I mean, these are, you see, this object is what you would call a function of k, right? This is a functional equation on a restriction on functions of k. Anyway, yeah. So the point is, you use more information here. You use the information that this is only a function of k. There's nothing. There's no other object in the theory. There's nothing like I don't know, an epsilon or something that epsilon mu or anything that can have that can affect this. So the only vector, the only Lorentz object that is of relevance is k mu, and then of course the constant one, delta mu, right? So then this equation uniquely defines this. All right, so the original word identity is a relation for the vertex, for this vertex, right? For the vertex of interaction of a photon with a fermion and antifermion, with an electron and positron. Right? So this is the classical vertex of the theory. Now at the quantum level, this becomes some quantum corrected vertex, right? And I want to obtain an equation for it, right? And then this is also part of the effective action. So there's a term here, A mu classical, psi bar classical, psi classical, right? This is A mu, this is psi bar. So times gamma mu alpha beta. Okay, and so this is gamma 3. And so I want to write an equation for this, and you see, for that I need to take 3 derivatives with respect to a mu, psi, and psi bar of gamma. And I already have an equation. I already have one derivative with respect to a mu, and one derivative with respect to psi, and one derivative with respect to psi bar. But it turns out that it's useful to take derivatives with respect to psi and psi bar, because then I can also cancel these psi and psi bars and get a non-trivial relation. So the equation of motion, the equation that we consider is taking derivative with respect to psi classical beta of z, psi classical gamma, no, alpha of y, of this world Takahashi or these I understand. And then put, of course, a equal to psi bar equals 0. And by taking the derivative with respect to psi and psi bar, then clearly this first term goes away. This is just linear in A, so this goes away under the derivatives. And then I'm left on the left-hand side with minus v dx mu then the third derivative of gamma with respect to a mu classical of x, psi classical beta of z, and psi bar classical alpha of y at a equal psi bar equals 0. And then well, let me write it like this: equal to, so rather than equal 0, I want to write it as equal to IE. And then I have to take here still a derivative with respect to psi on 1 over psi bar. To get something non-zero after I put psi equal psi bar equals 0, I have to hit with the derivative with respect to psi here and psi bar here. So I get IE d2 gamma d psi classical beta of z wait a minute, I think no, that's fine. So then there would be d psi bar classical of x. So this was at some x, right? And then this also had some index, let's call it gamma. But then I differentiate with respect to psi bar classical alpha let me see, I think I have something wrong here. Beta classical of z, alpha classical y. No, it's let me do this more precisely. So in the first term I have, no, it's like this. I think I have a minus sign wrong somewhere. All right. So I have IE, the second derivative with respect to psi. And now, in the first term, I keep this derivative with respect to psi bar alpha. But then, derivative with respect to psi then I have derivative with respect to psi gamma of x. No, it's not wrong. It's the order of derivatives, of course. Yeah. So I write it in this order, which means so then the final term is d psi classical of x gamma, d psi beta classical of z. Okay, but in writing like this, let's see. So here I have beta psi bar, dd psi beta, dd psi bar alpha, dd psi gamma. And now I've went past psi bar. I went past 2 and then past one more. Yeah, so I get a minus sign. So I get this past 2 and then this past 1. So overall I have 3, I've switched 3 derivatives with respect to fermions, which are fermionic. So I switched 3, I made 3 switches of fermions, so overall minus sign. And then this thing here is delta gamma beta, delta x minus z. So, and then the next term is plus IE d2 gamma d psi classical beta of z d psi bar classical alpha of. So now I want, in the second term, I want to consider this one, which is x. But then I have d psi bar classical gamma of x, d psi. This is d psi bar classical gamma of x, d psi bar classical alpha of y. Okay, and this is equal to delta alpha gamma, delta x minus z. But now the order. When I write this, I have d psi beta, d psi bar alpha, d psi bar d psi bar gamma. Sorry, here was gamma. And d psi beta, psi bar. Yeah, so now I have only one switch. So, in here I had this term with IE psi, but I also need to switch this to write psi bar on the other side. So that gives a minus sign, with this other minus sign gives plus. Okay, so all in all, we obtain let me put this first term, plus IE plus IE d2 gamma d psi beta of z d psi bar. So gamma is equal to alpha now of x delta x minus z minus d2 gamma d psi gamma, which is now equal to beta of x d psi bar alpha of y delta of x minus z. No, x minus y. Sorry. The first term this was x minus y. Now it's x minus z. All right, let's see if I got the same thing. ed z d psi bar classical x delta x minus y minus, yeah. All right, good. And let me write also the first term. So gamma d mu classical x d psi beta classical y of z d psi gamma classical y. All right. So this is the equation, but now we can call things as they are. So this is the photon, the electron propagator, so inverse propagator, SF minus 1 alpha beta of z minus x no, yeah. And then this is SF minus 1 alpha beta of y minus x. And then this is the photon fermion propagator, so gamma mu alpha beta x and y and z. Okay, so also I can go to momentum space to make it slightly better. Then derivative is minus derivative amounts to IP mu. And then we get the same I on the right hand side, so we'll cancel these two i's. So we get P mu gamma 3, let's say, gamma 3 mu alpha beta. Now this of P mu, and the other ones will be called Q2 and Q. So P, Q2 and Q1 is equal to E. Now SF minus 1. Delta function Fourier transform is 1. And then in here we get Z, which is associated with Q2. And here we get Y, which is associated with Q1. So this was associated with X, this was Y, this, oh sorry, no, this is Y, this was Z. All right, and so you see that we can write this diagrammatically. So this thing is a vertex, as I said. this is a vertex between a fermion momentum q2 and an antifermion with momentum q1 and a gauge field with momentum p. But if I multiply here with p mu on this side, what I get is E times this inverse propagator SF minus 1 minus so this I'll put here with Q2 and here with Q1. Okay, so this is the diagrammatic representation of this equation. So this is still an equation derived from gauge invariance. So this is still an example of the effect of gauge invariance on the quantum theory. And again, we see the same kind of theory. This restricts the possible tensor structure of the thing, because it tells us that by contracting the index mu with p, I get a particular scalar related to this. Right? So now, well, in some sense, that means that it's is this. So gamma mu is this times p mu plus a piece that is transverse, which means p mu on it is equal to 0. Okay. All right. Yeah, so that's the only thing I want to say. Of course, I've shown you 3 examples. Now you can take other derivatives of this and put things to 0. You'll get, you could write an equation where you take more derivative with respect to psi, or some combination of derivative with respect to psi and with respect to a. It's just that most of them will be kind of trivial, so the relevant ones are the ones that I already described in here. All right, so that's everything I want to tell you today. Do you have any questions? I'm sorry?
Because, for example, for me, this is the propagator, right?
Well, yes, but this is the connected, right? So the connected and the 1 pi are...
The connected for me would be this. Then this goes to 0 because of the... When I say this...
I'm sorry? No, okay. Depends what you mean by average. But if you divide by the normalization, then you get, this is the connected 2-point function.
So you divide, you get this person.
Connected 2-point function, connected 2-point function,
the
GC is equal to the path integral of a nu, divided by path integral of 1, right?
If I take the derivatives of the free energy, I get this at the bottom, right?
Right. So yeah, this is generated by the free energy. Okay. So this is the generating functional. The free energy is the generating function of the connected 2-point function, 2-point functions. But these things were what? Well, so these things are correlators, right? They're not, not physical in some sense, right? you cannot measure the correlator, especially not the one of gauge fields, right? But you can measure the two-point function comes from the quantum effective action, because that's what you get from the equivalent of the classical equation of motion, right? These are two different objects, right?
This object is this at the bottom, right? The connect.
This is the definition of the connected. I'm not sure what you're trying to write there. I'm not.
Take the derivatives.
I just don't like that. I'm not sure what that is. This is the connected two-point function.
But you get exactly this. So what else?
Yeah, that doesn't make sense to me. I mean, that actually makes no sense whatsoever. But this is the two-point function, connected two-point function.
Why does it make sense? Because if you take the
What's a nu? The one-point function of a nu.
It's the a mu inserted in the derivative.
No, in terms of diagrams. Write some
In
diagrams.
terms of diagram. Imagine the classical field, so the scalar field.
No.
Then this is.
Okay, so the classical field is one thing, right? So, but it's not what you wrote there. It's the
The scalar field is. You get.
Anyway. Yeah.
Because for me
Anyway, so that's it. The connected two-point function is this one, and it's a different object than the one. The connected two-point function is something that's not even though it's path integral, it's not physical. It's not related to an observable. Whereas this one, well, okay, not for gauge field. For gauge field, there's the issue of gauge bars, but otherwise, the 1pi part is something that you can measure by looking at the classical equation of motion. All right, good. Well, I think that's everything.